In this section of the course, we are going to discuss how to deal with text data in natural language processing. This directly ties into the previous section, which was on using RNNs for modeling sequence data. Of course, text is also sequence data, but there's a major difference between text sequences and the continuous valued sequences we were dealing with in the previous section. That difference is text is made of words, and words are categorical objects. In other words, they are not continuous. Suppose we're given a sequence of words. The quick brown fox jumps over the lazy dog. So x1 equals the, x2 equals quick, and so on. But here's the problem. We know that in order to calculate the output of an RNN unit, we have to multiply each x by the input to hidden weight, wxh. You can see that if x is a category, this is not possible. You might think, aha, I've seen this before. When I have categories, all I need to do is one-hot encode them. So for example, what you would do is create an array which has length equal to the size of our vocabulary. In other words, the number of words in the English language. Typically, we denote that with the capital letter V. So here's how we are going to one-hot encode a word. First, we're going to create a vector of size big V containing all zeros. Then we're going to create a mapping where we have, for each word, a corresponding integer starting from 1. So for example, the word A will get the index 1. The word AA will get the index 2. The word activation might get the index 100. And we do this for all other words, so we get all the way up to zoo, which maybe has the index 1 million. Finally, once we have a map for each word to an integer, we simply set that corresponding index to 1. So as you can see, all of these vectors are a bunch of zeros with only a single 1 at a unique position. So thus, our final one-hot encoded word vector becomes a vector of mostly all zeros except with one 1. So what happens after we do this? Well, now we can go back to our usual scenario. If we have a sequence of t words and each of them becomes a vector of size v, then we have a t by v matrix, which represents our sequence. This is the same shape as a generic t by d sequence. We can then pass this into our recurrent neural network as normal. So let's do a very simple example. Suppose we had the sentence, I like cats. This is a sequence of length 3 because this sentence has 3 words. This might turn into the sequence of vectors 0001, 0100, 1000. For this simple example, we've assumed that our vocabulary only contains 4 words, which of course is much smaller than a real English language dataset. But there are some problems with this approach. Some English language datasets have about 1 million possible tokens or words. That would lead to an extremely large one-hot encoded feature vector, which means that your weight matrix would also be very large. So in other words, you have a t by v matrix, but v is a very big number. In actuality, the English dictionary contains only about 200,000 words, so it really depends on how you split up your words and where you obtain your vocabulary from, but this is still a significantly large number. Here's another problem with this approach. Remember that we would like our input features to have some structure. If you recall, one of the earliest rules we encountered was machine learning is nothing but a geometry problem. This rule relies on the fact that there's geometrical structure in our data. Data vectors from the same class are probably close to each other. But what do one-hot encoded feature vectors look like? Well, if we take any two one-hot encoded feature vectors and we calculate the Euclidean distance, we will always get the square root of 1 squared plus 1 squared, which is just the square root of 2. It doesn't matter which 2 words we select because they are all one-hot encoded. For example, the distance between cat and feline would be square root of 2, but the distance between cat and airplane would also be square root of 2. In other words, this data has no useful geometrical structure. So what can we do instead? Well, it would be nice if, for each word, we could map them to a d-dimensional vector. Luckily, we have just the tool for this. It's called an embedding layer. Now you might be wondering, how can we actually make these vectors have a useful structure? We'll get back to that later, so stay tuned. But before we discuss that, I want to show you a little coding trick. So consider what happens if we multiply a one-hot encoded vector with a weight matrix. Let's suppose the vector is just three-dimensional, 1, 0, 0, and the weight matrix just contains the numbers 1 up to 9. You can verify for yourself that when we multiply this vector by this matrix, we get the vector 1, 2, 3. Now consider the one-hot encoded vector 0, 1, 0. What happens when you multiply this vector by the same weight matrix? We get the vector 4, 5, 6. Now consider the one-hot encoded vector 0, 0, 1. What happens when we multiply this vector by the same weight matrix? We get the vector 7, 8, 9. So what is the pattern we see? If the index in the one-hot encoded vector, which was set to 1, was 1, then we get the first row of the weight matrix. If the index was set to 2, then we get the second row of the weight matrix. If the index was set to 3, then we get the third row of the weight matrix. In other words, if we one-hot encode the integer k and multiply it by the weight matrix, all that's really doing is selecting the kth row of the weight matrix. So here's a shortcut. The old way of doing this took 2 steps. First, we had to create a one-hot encoded vector and set the kth entry to 1. Second, we had to multiply this one-hot encoded vector by the weight matrix. The shortcut way of doing this takes only 1 step. We simply index the weight matrix at the row k. This is obviously much more efficient than creating a one-hot vector and then doing matrix multiplication. Think of it this way. Indexing an array is O of 1, that's constant time. But how long does it take to create a one-hot vector and then do matrix multiplication? If your vector is of size v, and the weight matrix is of size v times d, then this is O of v times d. So this is exactly what the embedding layer in PyTorch does. Instead of doing all the work yourself to create one-hot encoded vectors, the only step you need to do is map your dataset with sequences of words into a dataset with sequences of word indices. Now that you have only integers, you can use an embedding layer to map each word's integer to a corresponding word vector. From there on out, your sequence becomes a T by D matrix, at which point you can use an RNN as you normally would. Conceptually, you can think of the process like this. First, we have some sentence, a sequence of words. Let's say for simplicity's sake, it's I like cats. Then, this sequence of words becomes a sequence of integers. Obviously, it doesn't matter which integer we assign to each word, as long as they are unique. This is just like when we are doing classification. It doesn't matter if we set dog to 1 and cat to 0, or vice versa. They are just arbitrary assignments. Finally, we can use these integers to index an embedding matrix, which will convert each integer into a word vector. So in the end, what we have done is 2 steps. First, we converted words to integers. Second, we map those integers to vectors. One question you might have at this point is, we know intuitively that similar words should be closer together than dissimilar words. In other words, these feature vectors should exist somewhere meaningful relative to each other. For example, king should be close to queen, and car should be close to automobile, but queen should not be close to car, and king should not be close to automobile. So how can we make sure that that's the case? Luckily, this is the same story as with convolutional filters. Because they are just weights in a neural network, they all get trained automatically. There's nothing fancy you need to do. Now, there's one caveat to that, which is that what people often do is use pre-trained word vectors. How this works is, when they create an embedding layer, they set the weights to a set of pre-trained vectors that were obtained through some other method. Then they freeze this layer so that those weights are never changed. Typically, these word vectors are found through algorithms such as word-to-vec and glove. Now that is a deep topic in itself, so in this course, we are going to avoid discussing that. Instead, we will train embeddings like any other layer by letting gradient descent do its magic. If you want, you're encouraged to read the word-to-vec and glove papers, since they are generally pretty accessible. To summarize this lecture, here's what we discussed. First, we recognize that it's not possible to multiply a word by a weight matrix. There's no concept of multiplying words. Therefore, we needed to somehow convert words into a numerical representation. We first thought about one-hot encoding each word, but we soon realized why that would not be a good idea. First of all, it would take up way too much space. There are around 1 million possible tokens in the English language, so each word would take up 1 million numbers to represent, which is quite silly. Also, these one-hot encoded vectors are actually meaningless in terms of being feature vectors. This is because each word vector, if it's just a one-hot encoded vector, would be equal distances apart. So cat is the same distance to feline as it is to airplane, so that's not very useful. It doesn't allow us to really make use of the rule, machine learning is nothing but a geometry problem. And thus, we need a better way to convert words into vectors. This method is to take each word, turn it into an integer, and then use that integer to index an embedding matrix. This is much faster than one-hot encoding and then doing matrix multiplication. In this way, an input sentence consists of words, then becomes a T by D matrix of numbers, which you know an RNN can readily accept. We saw that this layer's parameters are trained just like any other layer, so nothing other than gradient descent needs to be done. Alternatively, if you are interested, you are welcome to read up on word-to-vec and glove, which provide different ways of initializing word embeddings so that you don't need to train them along with the rest of the neural network.